Every night, countless streams of light arrive at your eyes. Some began their journey a fraction of a second ago, bouncing off the walls around you. Others traveled for years across the darkness of space before finally reaching Earth. And some of the light entering your eyes tonight may have started its journey long before human civilization existed, crossing unimaginable distances through the silent emptiness between the stars. We often think of light as the ultimate traveler, the great messenger of the universe, constantly moving from one place to another. Yet hidden inside this familiar idea is a strange and unsettling question. Can light ever truly reach its destination? Or is the journey itself something far stranger than we have ever imagined? At first, the answer seems obvious. Of course, light reaches its destination. The light from the sun reaches Earth in about 8 minutes. The light from distant stars reaches our telescopes after traveling for years, or even millions of years. Every photograph ever taken appears to prove that light arrives somewhere. Yet physics has a habit of turning obvious answers into mysteries. The deeper scientists looked into the nature of light, the more they discovered that its journey may not resemble any journey we experience in our daily lives. To understand why, imagine standing beside a railway track. A train rushes past you at tremendous speed. Even if the train is moving incredibly fast, someone inside the train can still throw a ball forward. To you, the ball appears to move faster than the train itself because the ball's speed combines with the train's speed. This seems natural because it matches our everyday experience. Velocities add together. Motion stacks upon motion. For centuries, scientists assumed light worked the same way. Then something extraordinary happened. During the 19th century, experiments began revealing that light refused to obey these expectations. No matter how fast an observer moved, the speed of light remained exactly the same. It did not matter whether you moved toward the source of light or away from it. The measured speed never changed. Light always traveled at approximately 299,792 kilometers per second. This result was so bizarre that many scientists initially struggled to accept it. The puzzle remained unsolved until the arrival of one of the most revolutionary ideas in human history. In 1905, a young patent clerk named Albert Einstein proposed something astonishing. Perhaps the speed of light was not changing because space and time themselves were changing. Instead of treating space as a rigid stage upon which events unfold, Einstein suggested that space and time were flexible. They could stretch, contract, and bend depending on motion. What seemed impossible suddenly became inevitable. The consequences of this realization were profound. Time could slow down, lengths could shrink. Clocks moving at high speed would tick more slowly compared to clocks at rest. These effects sound like science fiction, yet countless experiments have confirmed them. Satellites orbiting Earth experience measurable differences in time compared to clocks on the ground. Without correcting for these relativistic effects, modern GPS systems would quickly become useless. But hidden within these strange discoveries was something even more remarkable. The closer an object moves to the speed of light, the more extreme these distortions become. Time slows, distances contract, energy requirements increase dramatically. As an object approaches the speed of light, these effects grow without limit. According to the laws of physics, an object with mass can never actually reach light speed because it would require infinite energy. Light itself, however, exists in a different category. Photons possess no rest mass. They do not need to accelerate up to light speed because they are born moving at that speed. They emerge from stars, atoms, and countless other processes already traveling at the cosmic speed limit. This unique status places light in a realm unlike anything else in the universe. The implications become stranger when we try to imagine the journey from light's perspective. This is where our intuition begins to fail. Human experience evolved at speeds far slower than light. We move through life at walking speed, driving speed, airplane speed. Even the fastest spacecraft ever built travel at only a tiny fraction of light speed. As a result, our brains are poorly equipped to understand what happens near the ultimate speed limit of reality. Suppose a photon leaves the surface of a distant star. It begins a journey that will take millions of years, according to observers scattered throughout the cosmos. Entire species might evolve and disappear during that time. Continents might drift. Civilizations might rise and fall. Galaxies themselves might slowly change shape. Yet the mathematics of relativity hints at something extraordinary. For a particle traveling at light speed, the usual flow of time appears to collapse. This statement must be approached carefully because photons do not possess consciousness. They do not experience anything. Still, the equations reveal a remarkable truth. As velocity approaches the speed of light, time dilation becomes increasingly severe. At the exact speed of light, the equations suggest that the passage of time shrinks towards zero. The consequences are difficult to visualize because nothing in our experience resembles such a condition. Imagine a beam of light leaving a distant galaxy billions of light years away. From our perspective, that light spends billions of years crossing the universe. It travels through expanding space. It passes clusters of galaxies. It encounters regions where gravity subtly bends its path. The journey appears unimaginably long. Yet, from the strange viewpoint implied by relativity, something very different emerges. The entire distance may effectively collapse. Distance and time are deeply connected. As time dilates, lengths contract. The faster an object moves, the shorter distances become along its direction of motion. At everyday speeds, this effect is negligible. At speeds approaching light speed, it becomes enormous. For light itself, the path between origin and destination shrinks toward nothing. This creates a paradox that has fascinated physicists for generations. If distance contracts completely and time does not pass, what does it even mean to say that light travels? Travel normally implies movement through space across time. A traveler begins somewhere, spends time on a journey, and eventually arrives elsewhere. But light challenges every aspect of this definition. Perhaps when we say that light travels, we are describing reality from our perspective, rather than describing what fundamentally occurs. From our viewpoint, photons race across the universe. Telescopes capture their arrival after years or millennia of travel. Yet the deeper structure of space-time seems to suggest that origin and destination may be connected in a manner far more intimate than ordinary motion allows. This idea leads us toward one of the deepest mysteries in physics. Is light truly moving through space at all, or is something more subtle taking place beneath our familiar picture of reality? The answer will force us to question not only the nature of light, but the nature of distance, time, and existence itself. And as we continue our journey, we will discover that the destination of light may be far stranger than the darkness it crosses to reach it. In the next chapter, we will venture deeper into the strange world of relativity and explore what space-time itself reveals about a universe where the fastest thing in existence may never experience the journey we believe it takes. If light challenges our understanding of travel, then the true source of the mystery lies deeper than light itself. The real mystery is space-time, the invisible structure that governs every event in the universe. We often imagine space and time as separate things. Space is where objects exist. Time is what clocks measure. One provides location, the other provides duration. It feels obvious because it matches our everyday experience. Yet one of the greatest discoveries in modern physics revealed that space and time are not separate at all. They are woven together into a single fabric, a four-dimensional arena in which every event unfolds. To understand why this matters for light, it helps to step away from our human perspective. Imagine a universe with only space and no time. Everything would simply exist. Nothing could change because change requires time. Now imagine a universe with only time and no space. Events could occur, but there would be nowhere for anything to happen. The existence of reality as we know it depends on both dimensions working together. Space and time are partners in a cosmic dance, inseparable and interconnected. For centuries, scientists viewed space as a fixed stage. The stars, planets, and galaxies moved across this stage while time ticked forward uniformly for everyone. This was the picture described by Isaac Newton. It worked remarkably well for understanding falling apples, planetary orbits, and the mechanics of everyday life. But hidden within the behavior of light was evidence that this picture was incomplete. The problem emerged because light refused to cooperate with the assumptions of classical physics. Every attempt to measure its speed produced the same answer. No matter how observers moved, light always seemed to travel at exactly the same speed. This consistency appeared impossible. If someone drives toward a moving train, the relative speed between them changes. Why should light behave differently? Einstein realized that the speed of light was revealing something fundamental about reality itself. If the speed of light remains constant for everyone, then space and time cannot remain fixed. They must adjust. Observers, moving relative to one another, must experience different measurements of distance and duration. What one observer calls a meter, another observer may see as slightly shorter. What one observer calls a second, another observer may see as slightly longer. This sounds abstract, but the consequences are real. Imagine two identical clocks. One remains on Earth, while the other travels through space at enormous speed. When the traveling clock returns, it will show less elapsed time. This effect has been measured repeatedly. Time itself genuinely slows for objects in motion. The universe does not merely appear different, it actually behaves differently, depending on how one moves through space-time. As speeds increase, the distortions become more dramatic. A traveler moving at 90% of light speed experiences time noticeably more slowly than those left behind. At 99%, the effect becomes extreme. At 99.9%, entire years might pass for distant observers, while only weeks pass for the traveler. The universe begins to separate into different realities, all equally valid. This is one of the most difficult concepts to accept, because human intuition insists that there should be a universal clock ticking somewhere in the background. We want there to be a single now shared by everyone. Relativity tells us otherwise. The universe contains no master clock. There is no cosmic heartbeat synchronizing every event. Different observers carve reality into different slices of space and time depending on their motion. And this is where light enters the story once again. As an object accelerates closer and closer to light speed, something extraordinary happens. The flow of time along its path slows increasingly toward zero. Simultaneously, distances along its direction of travel contract. A journey that appears vast to a stationary observer becomes progressively shorter to the traveler. Imagine a spacecraft heading toward a star 10 light years away. From Earth, the voyage requires more than 10 years, even if the spacecraft somehow travels near light speed. But for those on board, the distance itself begins shrinking. The faster they move, the shorter the journey becomes. At sufficiently high speeds, what appear to be 10 light years may feel like only a fraction of that distance. This phenomenon is not an illusion. It is built directly into the geometry of space-time. The universe does not merely contain distances. It allows distances to depend on motion. For human beings, these effects remain small because our speeds are tiny compared to light speed. Even the fastest astronauts experience only minuscule time dilation. But for light itself, the implications become staggering. A photon crossing the diameter of the Milky Way appears to undertake a journey lasting 100,000 years from our perspective. During that time, entire civilizations could emerge and vanish. Species could evolve. Continents could reshape themselves. Yet, the mathematics points toward a reality where the photon's path becomes compressed in a way that defies ordinary imagination. Again, it is important not to think of photons as conscious observers. They do not possess awareness. But if we use relativity as a guide, the distinction between departure and arrival begins to blur. The vast gulf of space separating origin and destination may not be as fundamental as it appears. This idea becomes even stranger when we examine the largest scales of the cosmos. Tonight, as you look into the sky, some of the light entering your eyes may have originated billions of years ago. Certain photons began their journey before Earth existed in its present form, before animals walked across land, before complex life emerged, before our sun was even born. These photons have traveled through an evolving universe, witnessing the expansion of space itself, or at least, that is how the journey appears to us. The observable universe spans approximately 93 billion light years in diameter, distances so large that ordinary language begins to fail. Numbers lose meaning at such scales. We can recite them, but we cannot truly visualize them. Yet every piece of information we receive about the cosmos arrives through light. Every galaxy observed by astronomers, every nebula captured by telescopes, every black hole inferred through observation. All of it depends on photons reaching us from unimaginable distances. Light serves as the messenger connecting isolated regions of space-time. Without it, the universe would be almost entirely hidden. But the messenger itself raises profound questions. If the geometry of space-time compresses distances at light speed, perhaps our intuitive picture of photons wandering across enormous cosmic deserts is incomplete. Perhaps what appears to us as a multi-billion-year voyage is, in some deeper sense, something radically different. Some physicists have described this idea poetically. They suggest that for light, the universe has no depth, no duration, no separation. The beginning and end of its path become inseparable parts of a single structure. Whether this interpretation is literally correct remains a subject of debate, but the underlying mathematics reveals something undeniable. Space and time are not fixed containers. They are active participants in reality. They stretch, contract, curve, and reshape themselves according to motion and gravity. The universe is not a stage. It is part of the performance. And once we accept this, a remarkable possibility begins to emerge. Maybe the deepest mystery is not how light moves through space-time. Maybe the deepest mystery is whether space-time itself exists in the way we imagine. Because as physicists pushed relativity further and further, They encountered places where even Einstein's elegant picture began to break down, places where gravity becomes infinite, places where time seems to stop, places where the distinction between journey and destination may disappear completely. In the next chapter, we will descend toward those regions of extreme reality and explore what happens when light encounters the most powerful objects in the universe, black holes. There, the very meaning of reaching a destination becomes more mysterious than ever before. If there is any place in the universe where the journey of light becomes truly mysterious, it is near a black hole. These strange objects represent the ultimate victory of gravity over space and time. They are regions where matter has been compressed so intensely that space-time itself becomes severely distorted. To approach a black hole is to enter a realm where the ordinary rules of reality begin to bend, stretch, and sometimes appear to break entirely. Most people imagine black holes as cosmic vacuum cleaners, endlessly sucking everything around them into darkness. The reality is both less dramatic and far more fascinating. A black hole does not pull harder than any other object of equal mass. If our sun were somehow replaced by a black hole of identical mass, Earth would continue orbiting exactly as it does now. The difference lies not in the strength of gravity alone, but in the extreme way gravity reshapes spacetime near the black hole itself. Einstein's theory describes gravity not as an invisible force pulling objects together, but as the curvature of spacetime. Massive objects create dents in this cosmic fabric. Planets follow the curves created by stars. Moons follow the curves created by planets. Everything moves along paths determined by the geometry of space-time itself. A black hole is what happens when this curvature becomes so extreme that it forms a kind of cosmic trap. At the center lies a region called a singularity, a place where current physics breaks down. Around it exists a boundary known as the event horizon. This boundary is often described as the point of no return. Once anything crosses it, escape becomes impossible. Not even light, the fastest thing in the universe, can find a path back out. This immediately raises a remarkable question. If light cannot escape a black hole, what happens to its journey? Imagine a photon traveling through space. For millions of years, it crosses the cosmos, moving past stars and galaxies. Eventually, it approaches a black hole. From its direction and momentum, it appears destined to continue forward. Yet, as it enters the region where space-time becomes increasingly warped, its path begins to curve. The closer it gets, the stranger things become. To a distant observer, the photon appears to slow down. This statement sounds impossible because light always travels at light speed. Yet both descriptions are correct. Locally, the photon continues moving at its usual speed. But from the perspective of someone watching from far away, gravity stretches time itself. Clocks near the black hole tick more slowly compared to clocks far from its influence. This effect is known as gravitational time dilation. Near an event horizon, time slows dramatically. A second experienced close to the black hole corresponds to far more than a second for distant observers. The closer one approaches the horizon, the more extreme the difference becomes. Imagine watching a spacecraft descend toward a black hole. The crew aboard the ship notices nothing unusual at first. Their clocks tick normally. Their hearts beat normally. Conversations proceed as usual. Yet from your distant viewpoint, something extraordinary occurs. The spacecraft appears to move more slowly. Its signals arrive increasingly delayed. Its clock seems to tick at an ever-reducing rate. As it approaches the event horizon, the spacecraft appears frozen. It never quite seems to cross. The image becomes dimmer and redder, as its light loses energy, climbing out of the black hole's gravity. Eventually, it fades from view entirely. To the distant observer, the crossing never appears to happen. But for the crew, it does. They continue inward. This is one of the strangest consequences of relativity. Two observers can witness radically different versions of the same event, and both perspectives remain valid. Now imagine replacing the spacecraft with a photon. What does it mean for light to approach a place where time itself appears to stop? The answer is not simple because light already occupies a unique position within space-time. Throughout this journey, we have explored the idea that photons do not experience time in the way ordinary objects do. Their paths connect distant events in a manner that challenges our intuitive understanding of travel. Near a black hole, this mystery deepens. The event horizon is not merely a location in space. It is also a location in time. Beyond it, every possible future path leads inward. The geometry of space-time becomes so distorted that moving away from the singularity is no longer an available direction, just as moving backward through time is not an available direction for us. To understand this, imagine standing on a river flowing toward a waterfall. If the current moves slowly, you can swim upstream. If the current grows stronger, swimming becomes more difficult. Eventually, there comes a point where the river moves faster than you can possibly swim. Beyond that point, every path leads toward the waterfall. The event horizon functions similarly. Space itself is flowing inward, not because some force drags objects along, but because the structure of space-time allows no alternative future. Light, despite its incredible speed, cannot overcome this geometry. And so the ultimate traveler reaches a place from which no destination beyond remains accessible. Yet even this is not the end of the mystery, because black holes force us to confront a deeper question. What exactly is a destination? In everyday life, a destination is simply the endpoint of a journey. You leave home, you travel, you arrive somewhere else. Beginning and end are clearly distinct. But relativity suggests that space-time already contains both the beginning and end of every path. Events are connected through geometry. The universe is not merely unfolding moment by moment. Instead, past, present, and future form a single interconnected structure. Some physicists compare this idea to a completed map. Imagine looking at a road drawn on paper. The start of the road and the end of the road both exist simultaneously on the map. The traveler experiences movement along the route, but the route itself already exists as a whole. This perspective is sometimes called the block universe. In this view, time does not flow in the fundamental sense we perceive. Instead, every event occupies its place within space-time, much like cities occupy locations on a map. If this picture is correct, then the journey of a photon becomes even more peculiar. The emission of light from a distant star and its eventual absorption elsewhere may not be separate events connected by motion alone. They may be parts of a single space-time structure. The photon's path exists as a complete connection between origin and destination. Its entire history forms one continuous thread woven into the fabric of reality. Black holes amplify this idea because they reveal how flexible time truly is. They demonstrate that duration depends on a perspective. What seems like an eternity from one viewpoint may correspond to a brief interval from another. Near the event horizon, distinctions between before and after begin to lose their familiar meaning. And if such distinctions can blur near a black hole, perhaps they are not as fundamental as we assume anywhere in the universe. This realization leads us toward an even more unsettling possibility. What if the journey of light is not primarily a story about movement? What if it is a story about connection? What if photons do not simply travel from one place to another, but instead link distant events across spacetime in a way that transcends our ordinary notion of distance? To explore that possibility, we must leave the world of black holes and enter the strange domain of quantum physics, where light reveals another side of its nature, a side so bizarre that even Einstein himself struggled to accept its implications. In the next chapter, we will discover why a single photon can behave as though it explores multiple paths at once, and how this quantum mystery may completely transform our understanding of what it means for light to reach a destination at all. By the early 20th century, physicists believed they were finally beginning to understand light. Einstein had revealed how light was woven into the structure of spacetime. Relativity explained why its speed remained constant and how time and distance changed for moving observers. It was one of the most successful theories ever created. Yet just as scientists began feeling confident, light revealed another secret. And this secret was arguably even stranger than relativity itself. The mystery began with a simple question: what exactly is light? For centuries, the answer seemed straightforward. Sometimes light behaved like a wave. It spread through space, interfered with itself, bent around obstacles, and produced beautiful patterns when passing through narrow openings. These behaviors appeared impossible to explain if light consisted merely of tiny particles. Waves seemed like the obvious answer, yet other experiments revealed something completely unexpected. Light also behaved as though it arrived in discrete packets, later called photons. It could strike matter in individual bursts. It could transfer energy in tiny quantized amounts. In some situations, light resembled a wave. In others, it resembled a particle. The deeper scientists looked, the less either description seemed sufficient. The famous double-slit experiment brought this mystery into sharp focus. Imagine a barrier with two narrow openings cut into it. Behind the barrier sits a screen capable of recording incoming light. If light behaves purely as a stream of particles, we would expect two bright bands to appear on the screen, one behind each slit. The particles would simply pass through one opening or the other. If light behaves as a wave, however, the result is entirely different. Waves emerging from both slits overlap and interfere with each other, producing alternating bright and dark regions. This interference pattern is exactly what scientists observed. At first, this seemed to confirm the wave theory. Then someone asked a deeper question. What happens if photons are fired one at a time? Surely a single photon cannot interfere with itself. Surely it must choose one slit or the other. Yet when researchers performed the experiment using individual photons, something astonishing happened. Each photon arrived at the screen as a localized particle. It produced a single point of impact. But after many photons accumulated, the interference pattern gradually emerged once again. Somehow, the behavior of countless individual photons recreated the pattern expected from waves. This result shattered classical intuition. It seemed as though each photon was behaving like a wave while traveling, and then suddenly behaving like a particle when detected. The situation became even stranger when scientists attempted to determine which slit each photon actually passed through. The moment they measured the path, the interference pattern disappeared. The photon now behaved like an ordinary particle choosing a single route. Yet when the measurement was removed, the wave-like pattern returned. It was as if reality itself changed depending on how the experiment was observed. Many interpretations have been proposed over the decades, and physicists continue debating their deeper meaning. But one way of visualizing the phenomenon became especially influential. Developed by the physicist Richard Feynman, it suggests something almost impossible to imagine. According to the mathematics, a photon does not simply travel along one path from its source to its destination. Instead, it behaves as though it explores every possible path simultaneously. Not just the obvious routes, every possible route, the shortest path, the longest path, paths that curve, paths that wander, paths that seem absurdly inefficient. The equations describing quantum behavior treat all possible paths as contributors to the final outcome. Most cancel each other out through interference. Only certain paths reinforce one another strongly enough to determine what we observe. The result is that light appears to travel along an efficient route, yet beneath the surface, the mathematics suggests a far richer process. This idea sounds like science fiction, but it produces extraordinarily accurate predictions. Quantum electrodynamics, the theory built upon these principles, is one of the most precise scientific theories ever developed. Its predictions match experiments to astonishing levels of accuracy. Yet accuracy does not necessarily produce understanding. Even Feynman himself famously admitted that nobody truly understands quantum mechanics in the ordinary sense. The equations work beautifully. The intuition does not. Now pause for a moment and consider what this means for the question guiding our entire journey. Can light ever reach its destination? Classically, the answer appears obvious. A photon begins at one point and travels through space until it arrives elsewhere. The process resembles throwing a ball across a field. The ball follows a trajectory from start to finish. But the quantum picture challenges this narrative. If a photon explores every possible path, then perhaps the destination is involved in the process from the very beginning. The final outcome helps determine which possibilities survive and which disappear through interference. The entire journey becomes something more holistic than our everyday concept of motion. Instead of imagining a photon as a tiny object moving through empty space, some physicists prefer to think of it as part of a probability structure extending across space-time. The photon's behavior is described not merely by its position, but by a wave function containing information about possible outcomes. This wave function evolves according to mathematical rules until an interaction occurs. And here lies another mystery. The destination itself plays a crucial role. A photon does not simply exist in isolation. Its story is completed only when it interacts with something else: a detector, an atom, a molecule, a retina in a human eye. Without such interactions, the familiar concept of arrival becomes surprisingly difficult to define. Imagine a photon leaving a distant star billions of years ago. Throughout its journey, we often picture it racing across empty space toward Earth. Yet quantum theory encourages a different perspective. The photon's behavior cannot be fully described solely by its departure. Its eventual interaction is equally important. The beginning and end become inseparable parts of one quantum process. This idea becomes even more fascinating when we consider how enormous the universe truly is. Between galaxies stretch vast regions of near emptiness. Photons travel through these regions for millions or billions of years. During that time, stars explode, galaxies collide, and entire cosmic structures evolve. Yet the quantum description remains intact. The photon's possibilities continue unfolding until interaction finally occurs. The universe itself becomes part of the calculation. Every gravitational field influences the paths. Every region of space-time contributes. Every possible route enters the mathematics. What appears to us as a single beam of light may actually represent an unimaginably rich tapestry of possibilities woven together across the cosmos. And if that sounds strange, the next step is stranger still, because quantum physics eventually revealed phenomena suggesting that particles separated by enormous distances can remain connected in ways that defy classical explanations. Connections so deep that Einstein famously referred to them as spooky action at a distance. These phenomena challenge not only our understanding of travel, but our understanding of separation itself. Perhaps the deepest assumption behind our question is that origin and destination are truly separate places. Perhaps we assume that light must cross a gap because the universe consists of disconnected regions, linked only through movement. But what if that assumption is wrong? What if the universe is fundamentally more connected than it appears? What if the distinction between here and there, between source and destination, between departure and arrival, emerges from a deeper reality in which everything is already linked together? In the next chapter, we will explore quantum entanglement, the phenomenon that forced physicists to rethink the meaning of distance itself, and discover why the journey of light may reveal that separation is one of the greatest illusions the universe has ever created. One of the most comforting assumptions in everyday life is the belief that things are separate. You are here, a distant star is there, a mountain stands far away, another galaxy exists unimaginably farther still. The universe appears divided into locations, each separated by distance. Everything we experience reinforces this idea. If you want to reach another city, you must travel. If a signal is sent across the world, it takes time to arrive. If light leaves a star hundreds of light years away, centuries must pass before it reaches Earth. Separation seems fundamental. Distance seems real. The universe appears to consist of isolated places connected only through journeys. Yet, throughout the 20th century, physics uncovered clues suggesting that this picture may not tell the whole story. The first hints emerged from the strange behavior of quantum particles. Scientists discovered that certain particles could become linked through a process now known as quantum entanglement. Once entangled, the particles behaved as parts of a single system, even when separated by enormous distances. This was not merely a matter of hidden communication or ordinary correlation. The mathematics suggested something much deeper. The particles could no longer be fully described independently. Their properties became intertwined in a way that treated them as aspects of one larger reality. To understand why this shocked physicists, imagine creating a pair of perfectly connected coins. You place one coin in a box and send it to the moon. The other remains on Earth. Years later, someone opens the lunar box and discovers the coin landed heads. Instantly, you know the Earth coin must be tails. At first glance, this seems ordinary. The outcome was determined from the beginning. Quantum entanglement is different. Before measurement, the properties are not simply hidden, waiting to be revealed. Instead, quantum theory describes them as existing in a shared state that does not assign definite outcomes in the classical sense. Only when measurements occur do specific results emerge. Yet the correlations between those results remain astonishingly precise. Experiments have repeatedly confirmed this behavior. Particles separated by kilometers. Particles separated by satellites orbiting Earth. Particles whose correlations continue matching the predictions of quantum theory with extraordinary accuracy. Again and again, nature refuses to behave according to our classical expectations. Einstein disliked this conclusion intensely. He believed that reality should possess local causes. Information should not appear to leap instantly across space. there should be hidden variables explaining the observed behavior. Together with his colleagues, he proposed thought experiments designed to demonstrate that quantum theory must be incomplete. For decades, physicists debated the issue. Then experiments arrived. One by one, they favored quantum mechanics. The universe appeared to side against Einstein. Today, entanglement remains one of the most thoroughly tested aspects of modern physics. Yet despite its success, its deeper meaning remains profoundly mysterious. The mathematics works. The predictions succeed. But understanding what is truly happening remains one of the greatest challenges in science. And this is where the story returns to light. Photons are among the most common particles used in entanglement experiments. Scientists routinely create entangled pairs of photons and send them in different directions. These photons may travel through optical fibers, through laboratories, or even through space itself. Measurements performed on one photon reveal correlations with the other that cannot be explained through classical ideas alone. The important point is not whether information travels faster than light. According to current physics, it does not. Relativity remains intact. No usable message can be transmitted instantaneously through entanglement. Yet the existence of these correlations suggests that the universe is organized in a manner very different from what our intuition expects. The deeper lesson is that separation may not be as fundamental as it appears. When we look at the night sky, we see distance everywhere. Stars separated by trillions of kilometers. Galaxies separated by millions of light years. Vast empty voids stretching between cosmic structures. The universe appears fragmented into isolated regions, connected only through movement. Quantum physics whispers a different possibility. Perhaps the apparent separations emerge from a deeper unity. Perhaps what we perceive as independent objects are manifestations of underlying relationships. Perhaps distance itself is not the most fundamental feature of reality. This idea sounds philosophical, but surprisingly, it has begun appearing in serious theoretical physics. Some modern researchers suspect that space-time itself may emerge from deeper patterns of quantum information. In this view, space is not the ultimate foundation of reality. Instead, space arises from networks of relationships connecting quantum systems. The implication is astonishing. If space emerges from relationships, then distance becomes secondary. What matters first is connection. Only later does the appearance of separation arise. Imagine looking at a map of airline routes. Two cities may appear geographically distant, yet if numerous direct flights connect them, they are effectively closer within the network. Conversely, two nearby locations with poor connections may be harder to reach. The structure of relationships matters as much as physical distance. Some physicists believe the universe may operate according to a similar principle. The geometry of space-time could emerge from deeper patterns of connectivity. What we call distance may be a consequence rather than a cause. What we call location may be a derived property rather than a fundamental one. And if that is true, then our question becomes far more profound than it initially appeared. Can light ever reach its destination? Perhaps we have been asking the wrong question. The question assumes that source and destination begin as separate entities requiring connection through travel. But what if they are already connected at a deeper level? What if the photon's journey is not fundamentally about crossing a gap, but about expressing a relationship that already exists within the structure of reality? To appreciate how radical this possibility is, consider how much of human history has been shaped by the challenge of overcoming distance. Entire civilizations developed transportation networks to connect separated regions. Ships crossed oceans, railroads crossed continents, airplanes shrank the world. Telecommunications allowed information to move across the planet. Again and again, progress involved bridging distances. Yet physics increasingly suggests that separation itself may not be as absolute as it appears. At the quantum level, relationships often take precedence over individual objects. At the relativistic level, space and time merge into a unified structure. At the cosmological level, every atom in your body originated within stars that died billions of years ago. Even biologically, you are connected to every living organism through a shared evolutionary history stretching back nearly 4 billion years. The deeper we look, the harder it becomes to draw sharp boundaries. Everything appears intertwined. Everything appears connected. The universe increasingly resembles a single unfolding process rather than a collection of isolated things. And nowhere is this more evident than in light itself. Every photon reaching your eyes tonight forms a connection between distant events. Some originated within nearby lamps, others bounced from clouds, others began inside stars. Every beam of light carries information linking different regions of space-time. Without photons, the universe would fragment into isolated darkness. Light is the great connector, the messenger binding distant places into a coherent whole. Yet the messenger may also reveal that the divisions it bridges are not as fundamental as we imagine. Perhaps the reason light can connect distant regions is because those regions already participate in a deeper unity. Perhaps travel is only the surface appearance of something more profound. Perhaps every photon is revealing a truth hidden beneath ordinary perception, a truth that becomes even more intriguing when we turn our attention to the largest structure of all, the universe itself. Because as cosmologists studied the expansion of the cosmos, they discovered something remarkable. Space is not merely a backdrop through which light travels. Space itself is changing, growing, stretching, evolving. And this raises a new mystery. If the universe expands while light is in motion, can a photon ever truly catch up to a destination that may be moving away faster than light itself? In the art's next chapter, we will leave the quantum world behind and journey into the expanding cosmos, where entire galaxies race away from one another, and the meaning of arrival becomes stranger than ever before. For most of human history, the universe was imagined as something stable. The stars appeared fixed. The constellations retained their familiar shapes. The heavens seemed eternal and unchanging. Ancient civilizations looked upward and saw a cosmic stage that appeared permanent, a backdrop against which the drama of life unfolded. Even after the rise of modern science, many astronomers assumed the universe itself existed in a largely static state. Galaxies might move, stars might be born and die, but the universe as a whole was expected to remain fundamentally unchanged. Then, during the 20th century, one of the most extraordinary discoveries in human history completely transformed our understanding of reality. The universe is expanding, not expanding into something else, not growing outward into a larger container. Rather, space itself is stretching. The distances between galaxies increase over time because the fabric of space-time itself is changing. This distinction is subtle, but it is crucial. Galaxies are not necessarily flying through space like fragments from an explosion. Instead, the space between them is growing. At first, this idea feels almost impossible to visualize because our brains evolved to understand movement through space, not the expansion of space itself. Imagine drawing dots on the surface of a balloon. As the balloon inflates, every dot sees every other dot moving away. None of the dots occupy a special center. None are moving across the surface in the ordinary sense. The surface itself is stretching. The expanding universe behaves similarly, although in 3 dimensions rather than 2. The discovery emerged through the observations of Edwin Hubble. During the 1920s, Hubble studied distant galaxies and noticed a remarkable pattern. The farther away a galaxy was, the faster it appeared to be receding. Light from these galaxies was stretched toward the red end of the spectrum, a phenomenon known as redshift. The simplest explanation was that space itself was expanding. Suddenly, the universe became dynamic. It had a history, a past, an evolution. And if expansion could be traced backward, then there must have been a time when everything was compressed into an extraordinarily dense state. This realization eventually led to the development of the Big Bang model, one of the foundations of modern cosmology. But hidden inside the expanding universe is a puzzle directly related to our question about light. Can light ever truly reach its destination if the destination itself is moving away? Imagine standing on a moving walkway at an airport. You begin walking forward. If you walk faster than the walkway moves backward, you make progress. If you walk at exactly the same speed, you remain stationary relative to the terminal. If the walkway moves backward, faster than you can walk forward, you never reach the end. Now replace the walkway with expanding space. Replace yourself with a photon. The situation becomes far more intriguing. Light always travels at the same speed locally. Every observer measuring nearby light obtains the same value. Yet, on cosmological scales, space itself expands while the photon travels. The destination is not simply sitting still waiting to be reached. The geometry of the universe changes throughout the journey. This creates situations that seem deeply counterintuitive. Some galaxies are so distant that the space between us and them expands faster than light. At first glance, this sounds like a violation of relativity. How can anything recede faster than light? The answer lies in understanding what relativity actually restricts. Relativity limits motion through spacetime. It does not limit the expansion of spacetime itself. A galaxy can appear to recede faster than light because the intervening space is stretching. No object is locally breaking the cosmic speed limit. The result is astonishing. There are regions of the universe from which light emitted today may never reach us, no matter how long it travels, no matter how much time passes. The expansion of space continually increases the separation. The destination retreats faster than the photon can close the gap. This boundary is known as the cosmic event horizon. Much like the event horizon of a black hole, it marks a limit beyond which certain events remain forever inaccessible. Think about what this means. At this very moment, stars may be shining in distant galaxies. Entire civilizations, if they exist, may be observing their own skies. Planets may orbit suns. Life may emerge and evolve. Yet some of those events will remain permanently hidden from us. Not because the light is too weak, not because our telescopes are insufficient, but because the structure of space-time itself prevents the journey from ever being completed. The photon leaves. The destination exists. Yet the connection is never established. In a sense, the journey fails before it begins. This realization forces us to confront a strange feature of reality. We often imagine the universe as a place where enough patience can overcome any distance. Given sufficient time, a traveler could eventually arrive anywhere. A signal could eventually be received. Information could eventually spread. The expanding cosmos reveals that this intuition is not always correct. There are limits built into the architecture of space-time itself, regions forever disconnected, destinations forever unreachable. And yet, paradoxically, nearly everything we know about the universe comes from light that did succeed in reaching us. Every image captured by a telescope represents a completed journey. Every star visible in the night sky is a destination successfully connected to an observer. Every galaxy photograph is evidence of photons traversing immense stretches of space-time. The universe we see is a map drawn by successful arrivals. What makes this remarkable is the sheer age of some of these journeys. When you look at the moon, you see it as it was about 1 second ago. When you look at the sun, you see it as it was roughly 8 minutes ago. When astronomers observe nearby stars, they often see years into the past. More distant galaxies reveal millions of years. The most powerful telescopes peer billions of years backward through cosmic history. In a very real sense, astronomy is time travel through observation. Light carries the past forward. The universe reveals its history, photon by photon. And this leads to one of the most beautiful ideas in all of science. Every act of seeing is an encounter with history. You never observe anything exactly as it is now. You observe it as it was when the light began its journey. Even the face of a person sitting across a room is technically a tiny glimpse into the past, although the delay is far too small for human perception. The cosmos magnifies this principle to extraordinary scales. A galaxy 1 billion light years away appears as it existed 1 billion years ago. A galaxy 10 billion light years away appears 10 billion years younger. As telescopes reach farther into space, they simultaneously look deeper into time. Distance and history become inseparable. Space becomes a record of the past, and light is the messenger carrying that record. Yet there is something almost poetic hidden within this fact. Every photon arriving at your eyes tonight has survived an incredible journey. Some escaped violent stellar explosions. Some traveled through interstellar dust clouds. Some crossed vast cosmic voids. Some passed near galaxies whose gravity subtly bent their trajectories. Many traveled for longer than human civilization has existed. All of them overcame extraordinary odds to complete their connection. The universe is not merely filled with light, it is filled with successful journeys, threads linking distant events across incomprehensible scales, messages written into space-time itself. But the deeper we explore, the more another question emerges. If every observation depends on light arriving from the past, how can we ever know what reality looks like right now? Does a present moment even exist across the universe? Or is the idea of a universal now simply another illusion created by human perception? The answer takes us back to one of the strangest implications of relativity, an implication that challenges our deepest assumptions about time itself. Because before we can determine whether light reaches its destination, we must ask a more fundamental question. Does the universe even agree on when that destination exists? In the next chapter, we will explore the disappearance of the present moment and discover why the concept of now may be one of the most deceptive ideas ever created by the human mind. For most of the history of science, space and time were treated as the ultimate stage upon which reality unfolds. Everything existed somewhere. Every event happened sometime. Even Einstein's revolutionary theory of relativity, despite completely transforming our understanding of space and time, still assumed that space-time itself was fundamental. It could bend, stretch, warp, and evolve, but it remained the arena within which everything else occurred. Yet, over the last several decades, an increasingly radical possibility has emerged from theoretical physics. What if space-time is not fundamental at all? What if space and time are more like temperature, pressure, or sound, real phenomena that emerge from something deeper rather than existing at the most basic level of reality? This idea sounds almost absurd at first because space and time appear more fundamental than anything else we know. Every experience depends upon them. Every memory occupies time. Every object occupies space. It feels impossible to imagine a deeper layer beneath the very concepts that allow experience itself. And yet history repeatedly teaches the same lesson. What appears fundamental often turns out not to be. Ancient civilizations believed Earth was the center of the cosmos. Later generations believed atoms were indivisible. Even space and time themselves once seemed absolute before relativity shattered that certainty. Physics has a habit of revealing hidden layers beneath apparent foundations. One reason scientists began questioning the fundamental nature of space-time comes from a profound conflict between the two greatest theories ever developed. On one side stands general relativity, Einstein's magnificent description of gravity and space-time. On the other stands quantum mechanics, the astonishingly successful framework governing atoms, particles, and microscopic reality. Separately, both theories work beautifully. Together, they refuse to cooperate. Whenever physicists attempt to describe situations where both quantum effects and gravity become important, such as inside black holes or during the earliest moments of the universe, the mathematics begins producing infinities and contradictions. This suggests that both theories may be approximations of something deeper. Neither may represent the ultimate structure of reality. Instead, they could be different windows looking into a hidden layer that remains only partially understood. One of the most fascinating clues emerged from studies of black holes. Physicists discovered something shocking while investigating the relationship between gravity, information, and thermodynamics. Black holes appear to possess entropy. Entropy is often described as a measure of disorder or information content. What surprised researchers was that a black hole's entropy does not scale with its volume. Instead, it scales with the surface area of its event horizon. This seemingly technical detail led to a revolutionary idea known as the holographic principle. The holographic principle suggests that the information describing a region of space may actually be encoded on its boundary. Imagine watching a three-dimensional hologram projected from a two-dimensional surface. The image appears to possess depth, yet the underlying information exists on a lower dimensional structure. Some physicists began wondering whether the universe itself might operate similarly. The three-dimensional world we experience could emerge from information encoded on a more fundamental boundary. If true, space itself may be something like a projection, not an illusion in the sense of being unreal, but an emergent phenomenon arising from deeper informational relationships. Suddenly, the concept of distance becomes less obvious. Distance feels fundamental because we experience it directly. Yet, if space emerges from information, then distance may also emerge. 2 points are not separated because space exists between them. Rather, space exists because of the relationships connecting them. This inversion of perspective is difficult to grasp because it reverses our usual intuition. We typically imagine objects first and relationships second. Modern theoretical physics increasingly entertains the possibility that relationships come first and objects emerge later. Consider a social network. The significance of a person within the network depends not only on their individual existence, but on their connections. Remove enough relationships and the ego structure changes dramatically. In some theoretical models of quantum gravity, space-time itself behaves similarly. Geometry emerges from patterns of quantum entanglement. The fabric of space is woven from connections. If that idea sounds familiar, it should. Throughout our journey, we have repeatedly encountered hints that connection may be more fundamental than separation. Quantum entanglement challenged the classical notion of independent objects. Relativity challenged the idea of universal simultaneity. Cosmology revealed that distant regions of the universe share a common origin. Again and again, physics seems to push toward a reality where relationships matter more than isolated entities. Now imagine what this means for light. For centuries, we have pictured photons moving through space. They leave a source, cross a distance, and eventually arrive somewhere else. But if space itself emerges from deeper relationships, perhaps this picture is incomplete. Perhaps the photon's journey is not fundamentally about traversing space. Perhaps what we interpret as movement through distance reflects the evolution of underlying connections. The implications become extraordinary. Imagine reading a novel on a digital device. When you move from one chapter to the next, the text appears in a different location on the screen, yet nothing physically travels across a literary landscape. The story unfolds because information changes. The appearance of movement emerges from deeper processes occurring beneath the surface. Some physicists wonder whether reality may function similarly. Space and motion could emerge from changes within an informational structure more fundamental than geometry itself. In such a universe, asking whether light reaches its destination becomes surprisingly subtle. The question assumes the existence of a path connecting two distinct locations. But if locations emerge from relationships, then perhaps source and destination are not fundamentally separate. Their apparent separation could arise from the way deeper information is organized. A photon would not simply cross space. Instead, it would participate in the structure generating space. The journey would become an expression of connectivity rather than traversal. While these ideas remain speculative, they arise from serious attempts to unify our understanding of reality. Researchers working on quantum gravity, string theory, holography, and related fields continue exploring the possibility that space-time emerges from something more primitive. No final answer has yet emerged. The deepest layer of reality remains hidden. Yet the direction of investigation is fascinating. The closer physicists approach the foundations of nature, the less solid space and time appear. Concepts once regarded as absolute increasingly resemble emergent features of a deeper order. This realization invites a profound shift in perspective. Human beings naturally think in terms of objects moving through space over time. Evolution shaped our intuition to navigate forests, rivers, mountains, and social groups. Our brains evolved for survival, not for understanding the ultimate architecture of the cosmos. As a result, many of the universe's deepest truths feel counterintuitive. Light exposes this limitation more clearly than almost anything else. Its constant speed shattered classical notions of space and time. Its quantum behavior challenged our understanding of particles and waves. Its role in cosmology revealed the dynamic evolution of the universe. Its connection to information continues shaping modern theories about reality's foundations. Every attempt to understand light seems to reveal something unexpected about existence itself. And perhaps that is not an accident. Perhaps light occupies a unique position because it sits at the intersection of so many fundamental principles: relativity, quantum mechanics, information theory, cosmology. The study of light repeatedly becomes the study of reality. which brings us closer to answering our original question. Can light ever reach its destination? By now, the question hardly resembles the simple puzzle with which we began. We started by imagining photons traveling from one place to another. Along the way, we discovered time dilation, black holes, quantum uncertainty, entanglement, cosmic expansion, and the possible emergence of space-time itself. Each step transformed the meaning of the question, and yet one final piece remains. Because, before we conclude, we must confront the deepest perspective of all, not the perspective of photons, observers, or even space-time, but the perspective of the universe itself, if such a perspective can be said to exist. In the next chapter, we will pull back farther than ever before and explore what the journey of light reveals about reality as a whole, and why the distinction between departure and arrival may ultimately be one of the greatest illusions in the cosmos. If we step back far enough, beyond individual photons, beyond stars and galaxies, beyond even the concepts of space and time, a remarkable pattern begins to emerge. Throughout this journey, every attempt to understand light has gradually transformed into an attempt to understand connection. We began with a simple image, a beam of light traveling through darkness toward a destination. It seemed straightforward. Something starts here and ends there. A source emits. A destination receives. Between them lies a journey. Yet every layer of modern physics has quietly challenged this picture. Relativity revealed that time does not flow equally for all observers. Distances shrink and durations stretch depending on motion. The universe contains no universal clock coordinating events. Quantum mechanics revealed that particles do not always behave like localized objects following single trajectories. Entanglement suggested that separation itself may be less fundamental than relationships. Cosmology showed that space expands and evolves. Theories of quantum gravity hint that space-time may emerge from deeper informational structures. Again and again, the lesson has been similar. The universe appears less like a collection of isolated things and more like a network of interconnected processes. Perhaps this should not surprise us. After all, every meaningful thing we know depends upon relationships. A melody is not a collection of individual notes. It is the relationship between notes. A sentence is not merely a collection of words. It is the relationship between words. A galaxy is not simply a pile of stars. It is a gravitational relationship connecting billions of stars into a larger structure. Even your own identity emerges from relationships. The atoms within your body were forged inside ancient stars. The oxygen you breathe comes from living organisms. Your memories depend upon networks of neurons exchanging information. Every aspect of your existence arises through connection. The deeper we look, the harder it becomes to find truly isolated things. Reality appears woven together. Light may be the most visible expression of this truth. Every photon connects events that would otherwise remain separate. A star emits light. Millions of years later, a telescope receives it. A distant galaxy shines. Billions of years later, human eyes observe its ancient glow. Light forms bridges across space-time. It allows information to travel. It allows the universe to become visible to itself. Without light, there would be no astronomy. Without light, there would be no vision. Without light, vast portions of reality would remain permanently hidden. In a profound sense, light is what transforms disconnected events into a coherent universe. Consider the photons entering your eyes at this moment. Some may have bounced off nearby surfaces only nanoseconds ago. Others originated in distant lamps. If it is nighttime, Perhaps a few began inside stars, whose light crossed immense distances before arriving on Earth. Each photon represents a completed connection, a thread linking one event to another. And yet, when viewed through the lens of modern physics, these connections become stranger than they first appear. Think back to the idea of the block universe. If space-time exists as a complete four-dimensional structure, then a photon's emission and absorption are not separate events waiting to be linked through time. They already belong to the same space-time path. The journey exists as a whole. Or think about quantum mechanics. The photon's behavior cannot always be described as a tiny object following a single route. Instead, the mathematics involves possibilities, probabilities, and interference patterns extending across spacetime. The destination participates in the description. Or think about emerging theories, suggesting that geometry itself arises from deeper informational relationships. In such frameworks, source and destination may not be fundamentally distinct entities, separated by an independent space. Their apparent separation could emerge from the structure of underlying connections. Viewed from these perspectives, the journey of light begins to look very different. The traditional picture imagines a traveler crossing a gap. Modern physics increasingly suggests a picture involving relationships spanning a structure. Instead of movement being primary, connection becomes primary. This shift may sound subtle, but it changes everything. Imagine two points connected by a line drawn on paper. We normally focus on the points and treat the line as something secondary, linking them together. But what if the line is equally fundamental? What if the relationship is not merely a consequence of the objects, but part of what defines them? The universe increasingly appears to operate this way. Objects gain meaning through their relationships. Events gain meaning through their connections. Light gains meaning through the interactions it creates. This perspective becomes especially powerful when contemplating cosmic history. The atoms in your body were created through processes involving ancient stars. Those stars formed from clouds of matter produced by even earlier generations of stars. The hydrogen within your body originated shortly after the Big Bang. Every atom carries a history stretching back nearly 14 billion years. You are not separate from cosmic history. You are an expression of it. The same is true for every living thing, every mountain, every ocean, every galaxy. Reality is not a collection of independent fragments accidentally sharing the same universe. Reality is a continuous web of processes extending across space and time. Light is one of the threads holding that web together, and perhaps this explains why light occupies such a central role in physics. Whenever scientists investigate light deeply enough, they encounter questions about the structure of reality itself. Not because light is uniquely magical, but because light sits at the crossroads of so many fundamental principles. It reveals how information moves. It reveals how space-time behaves. It reveals how quantum systems interact. It reveals the history of the cosmos. Light acts almost like a guide, leading us toward deeper layers of understanding. Yet even after centuries of investigation, mysteries remain. We still do not possess a complete theory, unifying quantum mechanics and gravity. We still do not know whether space-time is fundamental or emergent. We still do not understand the ultimate nature of reality. And perhaps that is fitting, because every answer uncovered by science tends to reveal new questions beyond it. The universe is not a puzzle with a final, completed image waiting to be discovered. It is an endless landscape of understanding, where every horizon reveals another horizon beyond. Light embodies this perfectly. For thousands of years, People assumed light was simple. Then it became a wave, then a particle, then both, then something described by quantum fields, then a key to understanding space-time, then a tool for probing the origins of the cosmos. Each discovery expanded the mystery rather than eliminating it. And now we arrive at the edge of our journey. We have followed photons across galaxies. We have watched time slow near black holes. We have explored quantum uncertainty. We have questioned the reality of distance itself. We have ventured beyond space-time toward deeper possibilities. Only one task remains: to return to our original question and ask it one final time: can light ever reach its destination? In the concluding chapter, we will bring together everything we have learned and discover why the answer may be both yes and no, depending entirely on what we mean by a journey, a destination, and reality itself. After everything we have explored together, the question that began this journey feels very different from when we first asked it. Can light ever reach its destination? At first, the answer seemed obvious. Every sunrise appears to prove that it can. Every star in the night sky seems to confirm it. Every photograph, every telescope image, every moment of vision depends upon photons arriving somewhere. Light leaves a source, crosses space, and reaches a destination. The journey appears simple, yet the deeper we traveled into physics, the stranger that journey became. Relativity taught us that time is not universal. Clocks do not tick equally for all observers. Distances are not fixed. Space and time bend together into a single structure called space-time. For objects moving near light speed, time slows dramatically and distances contract. The closer we looked at light, the more the ordinary concept of travel began to dissolve. Then quantum mechanics complicated the picture even further. Photons refused to behave like tiny particles following simple paths. Instead, they revealed a reality filled with probabilities, interference, and possibilities extending across space-time. The destination seemed woven into the description from the beginning. The journey became something far richer than motion through empty space. Black holes showed us that time itself can nearly stop. Cosmic expansion revealed destinations that light may never reach. Entanglement challenged our assumptions about separation. Modern theories hinted that space-time itself might emerge from deeper informational relationships. Again and again, reality refused to conform to our intuitive picture of a traveler crossing a gap. And so we arrive at a fascinating conclusion. From our perspective, yes, light reaches its destination. Every photon that enters your eyes tonight completes a journey. Every signal received by a telescope completes a connection. Every beam of starlight arriving from deep space is evidence of a path successfully traversed. The observable universe is built from countless examples of light reaching somewhere. Yet, from another perspective, the answer becomes less straightforward. If time does not pass for light in the way it passes for us, what does the journey mean? If space-time exists as a complete structure, what does arrival mean? If source and destination are connected through deeper relationships, what does separation mean? The farther we follow the question, the more the distinction between departure and arrival begins to blur. Perhaps light does not simply travel through the universe. Perhaps light reveals the universe. Perhaps every photon is less like a traveler and more like a connection, a thread woven through space-time, a bridge linking events across cosmic history, a messenger carrying information between regions that would otherwise remain forever isolated. And perhaps the deepest lesson is not about light at all. Perhaps it is about reality itself. Human beings naturally experience life as a sequence. We are born, we grow older, We move through moments one after another. Everything appears divided into beginnings and endings, causes and effects, departures and arrivals. But the universe revealed by modern physics is often less concerned with separations than with relationships. The stars are connected to the atoms in your body. The photons entering your eyes are connected to events that occurred millions or billions of years ago. Your existence is connected to ancient stars that died long before Earth formed. Everything participates in a story stretching across nearly 14 billion years of cosmic history. The deeper we look, the more reality resembles a vast network of connections rather than a collection of isolated things. Light is one of the clearest expressions of that truth. It connects stars to planets, galaxies to observers, past to present, the universe to itself. Tonight, somewhere beyond the horizon, photons are leaving distant stars. Some will travel for centuries, some for millions of years. Some may cross vast stretches of intergalactic darkness long after humanity is gone. Their journeys will continue through an expanding cosmos filled with mysteries we have yet to imagine. And perhaps one day, somewhere, they will reach their destinations. Or perhaps, in a deeper sense, they already have. As you drift toward sleep, let that thought linger for a moment. The light from distant stars, the atoms within your body, the fabric of space-time itself, each part of a universe far stranger, older, and more interconnected than our everyday experience suggests. A universe where journeys and destinations may not be opposites, but different aspects of the same cosmic structure. Thank you for joining me on this journey through the nature of light, space, time, and reality. And if you enjoyed exploring these deeper questions about the universe, consider subscribing to Science Sleep Theory for more calm, immersive journeys into physics, cosmology, and the hidden mysteries of existence. Until next time, keep looking up, keep wondering, and sleep well beneath the ancient light of the cosmos.